Hey guys, welcome back. This is lesson 14. With lesson, well, obviously this lesson goes with along with the assignment. So I suggest watching this to help you with the assignment. It makes it a little bit easier. So last time we met, we talked about table J in the activity series. Just a little recap. The higher the element is on table J, the more active it is. The lower the element is, the less active it is. Really simple. Also, remember, once again, that H2 hydrogen is not a metal. Even though it is on the metal list, it is not a metal. So this is our do now for today. So according to table J, which metal is more active, C, R, or K? Once again, go back to this and we'll notice that K is a whole lot higher than CR, making it more active. And that's your explanation. For problem number 2, it says we have to write the half reaction, find out which species is reducing, and then which species, why it is related to table J. Now, just to do this real quickly, Zn has an oxidation state of 0. Cu has an oxidation state of 0. I'm only going to focus on Cu and Zn. But Cu over here would have an oxidation of +2. And then Zn over here would have an oxidation state of +2. Actually, I made one little boo-boo. Let me fix that. Cu will have an oxidation state of +1. So I just want to erase that one right here, and then I'll go ahead and put +2, +1 down, right? So when we look at this, I always like to focus on only the elements that go to 0 on the actual equation. If not, then I'll assign all the oxidation numbers and do all the rest. So we'll notice that Zn is going from 0 to +2, so that is oxidizing. And then Cu is going from +1 to 0, so that is reducing. And I've identified what is reduced. That is going to be Cu, right? And then let's go ahead and write our half reactions. I'm going to start from left to right. So Zn has 0. Then when we go to the right, it has Zn has +2. How many electrons were involved? But 2 electrons, right? For copper, we have on the left Cu +1. When we go on to the product side, Cu has 0. That does not look like a 0, but it's okay. You get the gist of it. There you go, 0. And then, how many electrons were involved? All but 1 electron. You can write 1 E minus, or you can write E minus. Explain why your answer to 2B was consistent with table J. Well, Zn is more active than Cu according to table J, which we can see here. Zn is more on top than Cu. So meaning this reaction is supported by table J because Zn is then going to replace Cu in the equation, which it does right here. For last one, explain using information from reference table J why this reaction is spontaneous. Well, the reaction is spontaneous because Fe is more active than H. If we go back here, is that true? Fe and then H. So yes. So Fe is more active than H. Now, remember, in this, they're not telling me why. They're not saying, is this spontaneous? They're telling me it's spontaneous. They want me to explain why. When it comes to Regents questions, when it comes to Regents questions, they mostly already are telling you the answer. They just want you to explain why that is the answer. Why is that so? Alright, so that's our do now. Now, today we're going to be focusing on Voltaic cells. When it comes to Voltaic cells, or when it comes to electrochemical cells, there's two. We have Voltaic cells and electrolytic cells. Today and Friday, we're going to focus on Voltaic cells. Monday and Tuesday, we're going to focus on electrolytic cells, right? So when it comes to Voltaic cells, I'm going to show you an image of it in a moment, but we need to be able to understand what it is. So Voltaic cells are run under spontaneous reaction, meaning one of the elements is going to be more active than one of the other elements, meaning it's going to change instantaneously. When that happens, it turns chemical energy into electrical energy. Now, this voltaic cells is another way we can say batteries. So these are the batteries you see in remotes. These are the batteries that you see in your cell phones. They are batteries. Voltaic cells is another way we call batteries. Now, when we have a voltaic cell, there's three parts of the cell. We have the cathode, the anode, and the salt bridge. Now, with the cathode, what you need to know is that the cathode is the element or the electrode that has the least active metal or non-metal. So it is the cathode that has the least active non-metal. Now, is the one that attracts the electrons. It is the positive electrode because the metal is less active. It is the positive electrode because the metal is less active. And it's where reduction occurs. This is where a reduction occurs. Now, to remember where reduction occurs, we come up with this little acronym right here. Red cat. Red standing for reduction, cat standing for cathode. So red cat, that is where reduction occurs. Then in the other electrode is everything opposite than a cathode. So the anode is where we have the more active metal, according to J. It's what loses electrons. So because it loses electrons, it's more negative because it's more active. It is more active, so it is the negative electrode. And it's where oxidation occurs, anox. It is where oxidation occurs. Now, besides those two, what differentiates a voltaic cell from an electrolytic cell is that a voltaic cell has a salt bridge. And a salt bridge just basically allows the electrons to flow and by preventing the buildup of charges. So these three parts are what makes up a voltaic cell. Now remember, a voltaic cell is all spontaneous. And basically we're discussing a battery. So let me show you an image of a voltaic cell. Now over here, the only thing that's missing from this voltaic cell is a salt bridge. So I'm going to go ahead and draw that in. Right? Because we got to have our flow of electrons. Alright. So, this is our voltaic cell. We have our anode and our cathode. How do I know that the zinc is my anode and the copper is my cathode? Not only because of the picture. If we go back to table J, our anode is our most active element. And zinc is more active than copper. Cu. So, this is going to be my most active. This is going to be my least active. This is also, the zinc is also going to be, the location of the zinc is my negative electrode, while the cathode is my positive electrode. My zinc is where I'm going to have oxidation occur. And my cathode, or the copper, is where I'm going to have reduction occur. Now look at this. Let's do a little quick review of oxidation and reduction. Oxidation is where we lose electrons, right? So we lose electrons. And then reduction is where we gain electrons. Right? So oxidation when we lose electrons, reduction is where we gain. So if I were to ask you, which way is the electrons going to flow? It's going to flow from the zinc to the copper, or the anode to the cathode, because that is where we anode is, or the zinc is losing the electrons, and the cathode is gaining the electrons. So my electron flow is going to go from the zinc to the copper. Right, let me just write flow right here. Alright, so that's where my electrons are going to flow. Now, since I labeled everything, the last thing I'm going to do just to practice this out is to write my half reactions. So, I know this is oxidation, right? And I see that I have zinc 2 plus here, and I know this is reduction, and I have copper 2 plus here. Now, one thing you need to be aware of is that when we're dealing with this, when we're talking about the element is usually an oxidation state of 0. So anytime we're talking about the element, it has an oxidation state of 0. So this is going to be helpful when I'm writing my um half reactions. So to write my half reactions, I know that I'm oxidizing, so I'm going to lose electrons. So I'm going to go from zinc 0 to zinc, leaving a space, to zinc 2 plus. Now some of you are wondering, how do you know it was 2 plus? Well, I know it's 2 plus from two different reasons. Because obviously the solution over here says zinc 2 plus. And also, if I look on the periodic table, the oxidation state for zinc is 2 plus, right? That tells me how many, remember, oxidation states tells me how many electrons I'm going to lose or gain. So, that's how I know how many electrons are going to be involved for zinc. Sorry. So now, I need to write in how many electrons were involved. Well, from 0 to 2 plus, only 2 electrons were involved, and they get written next to the element with the oxidation state. So there we go. This is our oxidation half reaction. Let's do the reduction. So reduction, we are starting off with zinc 2 plus, right? And then it gains electrons. So it becomes zinc 0. How many electrons were involved once again? 2 electrons. How do I know this? Well, I have 2 plus here. And also, if I look on the periodic table, copper's oxidation state is 2 plus. So here's our Voltaic cell. We've answered all the possible questions for it. Let's do one more practice. So, I know this is a Voltaic cell. How do I know automatically that this is a Voltaic cell? Well, I have my cell bridge right here. So I'm going to label B as CB. Then, now I have to identify my anode and my cathode using table J. Well, I have aluminum and copper. So let's go find out using table J which one is my anode and which one is my cathode. As long as you remember anode is more active or cathode is less active, you should be fine. Remember one or both. So aluminum over here is more higher than copper. So aluminum is going to be my anode. And just because I like putting everything out of the way, I know anode is negative, and I know that it is oxidation occurs here. So I've done majority of my labeling. And I know cathode, cobalt is my cathode because it's the least active. So red cat, because I know this is where reduction takes place. And this is my positive electrode, just because it has the least active metal. Alright, now that I have that, where's the flow of electrons going to go? Well, and Al, aluminum is going through oxidation, so it's going to lose electrons. Well, cobalt is going through reduction, so it's going to gain electrons. So my flow of electrons is going to be from Al to CO. Alright, brilliant. Now last thing we're going to do, we're going to write our half reactions. Once again, this is a solid by itself, so it's 0. These oxidation states are 0, and the other oxidation states that I'm going to be dealing with are down here. So aluminum is going to go from Al 0 because it's losing electrons to Al 3 plus, and then I need to remember that I'm going to write this down here. I need to remember that I'm dealing with 3 electrons, so it's going to be plus 3e minus. Sorry about the little breakup right there. And then over here, cobalt, we are starting with CO2 plus, because it's going to gain electrons, arrow, and then it's going to go to 0, cobalt 0, after it gains the 2 electrons because it's becoming more negative. But how many electrons were involved with that? Well, it's going to be 2 electrons, so plus 2e minus. And there we go. We've gone ahead, we've decided that this was a Voltaic cell because it has a salt bridge. We've identified our anode and our cathode. We've written where the electrons are going to flow from the aluminum to the cobalt. And we've also written